In this video, we're going to talk about vaporization and a little bit about condensation. So remember that molecules in substances such as liquids are never not moving. Liquids are constantly in motion, vibrating, rotating, and moving up, down, left, and right. And on average, every molecule, based on the temperature, has some kind of kinetic energy, and we have an average for that, and that's the average kinetic energy. But it is just an average. So some molecules have high kinetic energy, some molecules have low kinetic energy, right? And what happens is if you have molecules at the surface that have high kinetic energy, what can happen is that these molecules can break free of the intermolecular forces and break free from the liquid to form a gas. And this is called vaporization. And so the more surface you have, the more likely these molecules are going to be at the surface. And so the larger the surface area, the larger the vaporization, right? And when we turn a liquid into a gas, we call this vapor, right? So let's take a look at the thermal energy distribution in a liquid, and it's temperature dependent. So here on the y-axis we have fraction of molecules, x-axis is energy. So any molecule that has passed this dotted line has the amount of energy needed to become vapor. As you raise the temperature of your liquid, you are giving more kinetic energy to your solution, so there are a greater number of molecules that can escape if they're at a surface compared to a lower temperature. And if you keep raising the temperature, then you'll start boiling your liquid, which means that you don't have to be at the surface anymore to form a gas. You'll spontaneously form a gas, right? And the opposite of vaporization is condensation. So what happens is when you have vapor in the air, they will eventually crash into something. And when they crash into something, they will transfer their energy to whatever they crash into, which lowers their kinetic energy, and they can turn back into a liquid. So if you have a vapor and it crashes back into the liquid itself, then it'll form the liquid again, right? What will happen sometimes is that you'll have many vapor molecules hit a surface and they'll form their own liquid drop. You'll see this, you have a cool glass on a hot day. The water in the air will hit that cold glass, lose a lot of energy, and that's why you form water droplets on the outside, right? Condensation. Right? And like I said, vaporization, condensation are opposite. And if you have a container that is open to the world, the vapor molecules will leave the liquid and then they'll fly off. There's less of a chance of them hitting the liquid again. And so in an open container, vaporization is much greater than the rate of condensation. And so you lose liquid. So let's say over winter break, you left your coffee on your desk and there's coffee in there. Come back 2 weeks later, there's just going to be brown gunk left because all the liquid has vaporized and there was nothing left to condense into. But in a closed container, this is different. Vapor cannot escape. Vapor will still be around the liquid. And so what will happen is that the amount of molecules in the liquid becoming a vapor and the amount of vapor molecules becoming a liquid, that rate is eventually going to be the same. Right? So let's think about evaporation and condensation in terms of intermolecular forces. And so the weaker the attraction between molecules, that is, the weaker the intermolecular forces, less energy you need to vaporize, or the easier it is to vaporize. So that also means the less intermolecular forces, the more energy you need to remove from the vapor for it to condense. So the easier it is to vaporize, the harder it is to condense. So, like, just saying, and again, the weaker the attractive forces, the faster the rate of evaporation, right? And we have terms for this as well. If you're liquid and you are easily evaporated, you are called volatile. For example, gasoline or fingernail polish. While those that have strong intermolecular forces and do not form a gas easily are non-volatile. For example, motor oil is non-volatile. And let's actually look at the energetics of vaporization now. So when a molecule leaves the liquid, that was a high energy molecule. Therefore, your average kinetic energy, if you lose a high energy molecule, the average of everything that's left has to lower. And if your liquid does not get energy back into it, that means you have lost energy permanently, and therefore you've lost your temperature. Therefore, vaporization is endothermic process. You lose that energy. While condensation is an exothermic process. Now, vaporization requires input of energy to break free of all the other liquids, right? So to vaporize something, you need to put energy into it. That's why we boil water, to break free of the liquid, right? And the amount of energy you have to put into, or the amount of heat, is called the heat of vaporization, delta H vap, or the enthalpy of vaporization. So that is how much energy do we have to put in to vaporize 1 mole of liquid? And it's endothermic. We always have to put heat into our system to vaporize something. So delta H of vaporization is positive. And it's somewhat temperature dependent. So let's look at water here. Water at the boiling point has a delta H vaporization 40.7. At 25, it's 44. So at lower temperatures, it's harder to vaporize something, and so delta H vaporization is bigger. You have to put more energy into your system to vaporize it. And vaporization and condensation, they're opposite, but they're opposite processes. So the energy is opposite but different signs. So delta H vaporization is positive because it's endothermic. Therefore, condensation will be negative, but the same number. And let's just look at these delta H vaporizations. And you can see the things with stronger intermolecular forces. So water has hydrogen bonds. Rubbing alcohol also has hydrogen bonds, but not as strong as water. Water has a slightly higher delta H vape. And we look at acetone and diethyl ether, which are polar but no hydrogen bonds. Their delta H vape is much lower. Right? So that's it for this video. I'll see you in the next video.